My name is Carlos Trayero. I'm a professor of physics at UConn, and today I'm talking about my quantum computing company, QueHot. I want to submit to you that this is a radical new approach for quantum computing. So, as has been discussed already, the promise of quantum computer is that it promises unlimited power, unrivaled power, extreme sensitivity. There is a lot of applications. However, there is a huge barrier for this. The biggest barrier, money. It is expensive, it is difficult, but more importantly, perhaps, it requires a huge infrastructure. So I argue that there is a multi-billion-dollar vacuum here in creating agile, small quantum computers, a different solution to problems that exist nowadays. I argue that this problem is quantum FPGA. So what is an FPGA? An FPGA is a field programmable gate array. It has been introduced already, a couple of lectures before me. It is used completely, all over the place. If you drove your car today, you probably have about 50 FPGA built in your car. An F-35 fighter jet has about 500 of them built in. And the reason why is because the fastest processing unit that we know of for sensing. So the biggest company is Xilinx, and basically what I'm trying to say is that whenever you're talking about automation of any sort, you're talking about sensing. Whenever you're talking about sensing, you're talking about FPGAs. How is this happening? What is the traction in the quantum world? Well, as far as I know, there are no quantum FPGAs architectures in the world right now. So I argue the quantum FPGA will be the holy grail of sensing, and therefore of very sensitive and fast automation. Why? Because it's fast. We can use the parallel sensing. It is headless, and this is a very important point. Headless means that you can have the sensor and the processing of the information in the sensor itself. As we know, quantum computing qubits, as of now, have some of the best records in sensitivity for sensing. And there is also already some theoretical architectures that propose how to build these quantum FPGAs. So the market. Right now, the market is between $10 to $15 billion annually. It is expected to exceed to the $20 billion in the next decade. There are very few players, even in the classical world, there are very few players in the FPGA market. For example, AMD paid about $48 billion for Xilinx, the largest FPGA manufacturer in the world. That included a 1.7 stock conversion from Xilinx to AMD. What is the vision of my company? The vision of my company is to create headless quantum sensors that can detect and process the data in the sensor itself. That would allow us for a standoff detection. That is, you can detect processes that happen far away using hybrid photonics with a rapid topology changing and having no wires. That is, I have a blank platform that I can reprogram on every single laser shot. The advantage of my company is that we can operate at high temperatures, anywhere from 77 Kelvin, that's liquid nitrogen, all the way to room temperature. We can change the entire topology of the system in less than a second. Right now, we have about 1 millisecond. We have low operational noise, and other advantages. The progress so far is that we have a structural light in place. So this is the way it works. So like I said, we have a blank material, and we use a structural light to create light circuits, if you like, in a quantum material. We use nonlinear optics to program the qubits and to read the qubits, and which is why we have such a fast readout. We have demonstrated a single qubit gate, like I said, at room temperature. And I think we have probably the world record of quantum gates right now at 100 femtoseconds in time. So if we were to win this award, the ask would be to use material for tuning the quantum materials that we use right now to have longer interaction times, and also to tune the wavelength to be able to demonstrate that we can go from the visible all the way to telecom. Thank you.
It looks like you have some pretty big competitors. What would you say of the advantages you listed as your main advantage over?
I argue we have no competitors. So the quantum computer market right now is driven by mainframes. So I argue that we're in the 70s of quantum computing, where a computer were the size of this room. What I'm trying to sell is a very small, agile, a much smaller number of qubits sensing and processing platform that you can deploy in this very small applications, including, for example, but not limited to, routing and connection between very asymmetric platforms, say superconducting quantum qubits that use RF. RF is what uses to drive the qubits in our system, the control part of the qubit, to photonics, hybrid systems, which is the light that we use to program the qubits themselves. So I argue there is no competitor in our space.
To what degree have you been able to validate this methodology of creating a chip? So we have this, it's called metal organic chalcogenolate quantum materials. They are a single flake of this material, and we have been shown a single qubit gate right now. We can, as of now, probably produce up to 100 qubits. What we have not shown yet is entanglement between the different qubits, yet.
Hi, sorry, I'm just a little bit confused and coming back to our previous question. I guess maybe I'll just take a step back and ask, who wants this? Like, who is the ideal customer? Like, why, from the sensing side or from the kind of quantum computing interconnect kind of opportunity?
So I would say the space, any space company. For example, where you want to have, if you want to have, like Boeing is trying to develop, for example, quantum computers in space, either as a router or as a processor of information, capture of information, for example. And if you have two very asymmetric quantum computing architectures, let's say you have a solid state quantum computer, a superconducting quantum computer, that requires RF circuits. What controls the shape of the light in our quantum computer is RF. However, what imprints the circuit is light in the telecom regime. So you can have this as a switch or interconnection between two different very asymmetric quantum computers.
Okay, and across all the kind of architectures that are out there, or is it limited to just a few of them?
Say that again?
From the quantum computing architecture side, like how universal would it be?
So
from superconducting to photonic to
anything from RF to visible light. So we can cross-communicate those two across the entire spectrum.
Beyond the application of quantum computing, what other markets might this technology benefit?
So we have been discussing with bioengineering, for example. So because the materials that we use are very inert, you can use these flake materials in larger scale, for example, as biomarkers in the skin. So you can use the qubits imprinted in the skin, for example, as a very sensitive biomarker of, say, how the skin is developing as after burn, for example, which is now something that is very tedious to do. You have to take your bandages off and so on and so forth. So this is another aspect that we can do, like surface biomarkers.
Thank you very much, QueHot. Next up, Doublet Labs.